According to my clock, I guess it's about time to start. So, welcome everyone to the morning session for the last day. And so it's my pleasure to introduce Nikolai Reshetikhin, our first speaker today. We'll speak on the asymptotic behavior of character measures on large tensor products of irreducible finite dimensional representations of simple Lie algebras. So, thank you very much.
Thank you. Can you hear me well?
Yep.
Okay, good. Well, actually, maybe I should start with some kind of elephant that's hiding in the room. It's a very sad time, and I think I should mention this. I'm originally from Russia, and I'm a Russian citizen. And what is happening now in Ukraine is appallable. What can I say? It was shock for most of the country. And just, there are very few positive things about all this. I want to share with you two kind of pleasant moments. One is, I have a co-author, Olga Postnova. So she has some distant relatives in Karelia, which is eastern Finland, sort of that belongs to the Soviet Union after. So people there were shocked, and they simply don't understand what's going on. I talked to my distant relative in Orel, which is a city about 100 kilometers east of Ukrainian border. So, it's kind of central Russia, so very provincial, somewhat conservative city. And this relative of mine, he was an engineer at the polygraphic factory. He knows people, from the top to the bottom of the work chain. He said the whole city was in shock. Maybe 1% of some people who are super indoctrinated by the TV were positive about this. So it's a very sad thing for both countries. So I wanted to prepare something non-semi-simple, which would be more in the spirit of times. But I'm going to stick with semi-simple case, simply because it was kind of almost prepared for this occasion. Okay, so now back to math. So I'm talking from Tsinghua University, where I moved a year ago, and I should say it's a fascinating place. China is a fascinating country. It's those who never visited it in the last few years, I highly recommend to visit it. This is not the country that you saw maybe 20 years ago or even 10 years ago. So anyway, so now back to math. So I'm going to talk about asymptotic behavior of the distribution of irreducible components in large tensor products of simple Lie algebras. It's based on joint work with Olga Postnova and Vera Serganova. Olga is from St. Petersburg, Vera is from Berkeley. She was my colleague. So here is the plan. So I'll talk about statistics of invariant tensors first. Since this is a workshop and school on mathematical physics, so I will kind of mention some physics. So from the physics point of view, we're talking about the statistics of invariant tensors in, say, systems with n atoms of spin 1/2 or larger spin, and in the limit when the number of atoms goes to infinity. It's a problem with physical flavor, and problem with mathematical flavor is just take the nth tensor power of some finite dimensional irreducible representation of some finite dimensional simple algebra, and the question is, what is the limiting statistics when n goes to infinity? Now, you may ask how it is related to vertex algebras. It's related. It's not very direct relation. Say more direct relation would be if I would count the statistics of tilting modules in tensor powers of representations of, say, small quantum group or quantum group with divided powers, for example. So this is something that I was initially wanted to talk, but I'm talking about this. Soon there will be a paper by Anna Lachovska, Olga Pasnova, and Dmitry Solovyov about the quantum group with divided powers, but now it's just SL2. So what is it? So the way how it is related, this subject is related to vertex algebras is the following. People observed maybe 20 years ago so that if you take, say, many operators, say in quantum chromodynamics or in conformal field theory, but if you take a lot of them, then cumulative conformal dimension can be computed using some kind of transfer matrices associated with these long tensor products. So these are the works of Kazakov, Staudacher, and kind of physics community around these people. So that's where large tensor products kind of come together with vertex algebras. Okay, but from more physical point of view, it's a simple problem. So you have n atoms of spin 1/2. The space of states is C2 to the n. The action of SU2 is diagonal. And so what we have here from a mathematical point of view is the tensor product of n two-dimensional representations of SU2. We know very well that it decomposes into the direct sum of irreducibles. In physics terms, these are representations of spin L/2. So physicists say about spin L/2 because they prefer to think about SU2 rather as spin 3, spin group for SO3, which is why it's L/2. And then the multiplicity is given by Catalan numbers, which is simply the difference, certain difference of binomial coefficients. And that's the number of vectors which transform as spin L/2 representation. So if you want to study the statistics of these representations for large n, first of all, we have to fix some probability measure. And in representation theory, there are very interesting probability measures, and there is a whole subject of integrable probability that was developed very effectively recently, starting from the works of maybe Alshansky, then Borodin, Okunkov, so now it's Borodin, Corwin, and there is a whole group of people working on this. So these are various probability measures related to representation theory, but there is a very simple one and a very old one, if you will say that 19th century is old, and I misspelled the name. I think French people will kill me for this. It's Chiral. There is no S. So Chiral measure on a set of irreducible subrepresentations of semi-simple representation V is the following. Fix a decomposition of this representation into the direct sum of irreducibles. They will occur with some multiplicity. And then the probability will declare that the probability of ith representation is equal to the multiplicity times the dimension, times the dimension of the irreducible divided by the total dimension. Obviously, these numbers are non-negative, and obviously their sum is to whatever. is 1. So it's a probability measure. So one can think of this as a Boltzmann distribution on the space of invariant tensors in the absence of magnetic field. We will come to this in a moment. Originally, this distribution, this Chiral measure was invented by Chiral when he studied regular representations of Sm and other groups like this. But this is something that we can bravely call Chiral measure without any big mistake. So this is the, so as I said, it's a Boltzmann distribution for large n. So for SL2, it's equal to this, where these are the Catalan numbers. And the very natural question is, so what happened to this probability measure as n goes to infinity? And the answer is given by the following theorem, which is, it's a nice exercise for an undergraduate student of advanced undergraduate student or graduate student who want to learn these things. So just use the Stirling formula for binomial coefficients in Catalan numbers, and then you will arrive to the following theorem, that the probability distribution converges to this measure on the coset. If you take a dual space to the algebra SO3 and mod it out by the action of the group SO3. So what it means is that if you will take some test function G and take the expectation value of this function with the probability, with this probability measure, it converges to this expectation value for this not quite Gaussian, but looking very similar to Gaussian measure on radial parts of this dual space to the algebra. So, in other words, we can say that this probability measure converges weakly to this continuous probability measure. So it's a nice result. It's not difficult to derive it. So then let's change the probability measure in some natural way. So I already mentioned Boltzmann distribution. So we're talking about quantum system with the space of states C2 to the n. So the Boltzmann distribution is given by the density matrix, and well, we can choose the density matrix in the most natural way. It's e to the magnetic field times the projection of the spin to the third direction, divided over the normalization factor, which makes it trace 1, and by the definition, it's a non-negative operator. So what's the physical meaning of this? We can say that this H is really physical magnetic field divided by the Boltzmann constant and the temperature in the absolute Kelvin units, and that this whole measure is just the limit of this quantum density matrix, normalized quantum density matrix, for some Hamiltonian H, and the system is in magnetic field H physical. So anyone who learned physics will recognize this as a basic object. So what we really study now is the limit, the high temperature limit when the magnetic field also goes to infinity. So there are two forces that are acting against each other. If you take high temperature limit, we will get the uniform distribution if there is no magnetic field. And that's the Chiral measure. But if there is a magnetic field, so we have a force acting against each other. So magnetic field is trying to order all spins parallel to the magnetic field in a certain direction because we fix the sign of the magnetic field, it's positive. And the temperature is trying to disperse these spins as much as possible. So as a result, if we fix this ratio finite, we will get this distribution where the energy function is simply magnetic field times the spin operator. So that's about physics. So now, suppose that we have an SU2 invariant observable. So if we fix the decomposition of C2 to the n into, say, multiplicity spaces, tensor, these irreducible modules, these are the spaces of dimension, that is the multiplicity given by the Catalan numbers. So if an operator acting in this space is SU2 invariant, that means that it acts in the multiplicity space. So if we take the expectation value of this operator with respect to this density matrix, it's simply the trace of this operator against the density matrix. So we will have this expression. So we have the trace of f divided by ml times the character measure. And so, so this is the uniform measure on the multiplicity spaces. And so this expectation value, so with respect to, when we average with respect to this expectation value, first we have the measure on the, so this gives the measure, sorry, this gives the measure on the symmetry types. Okay, so, and then if you want to compute expectation values, then you have to compute this trace. And then you take the expectation values of these expectation values with respect to this measure. Okay, so in a sense, this is a deformation, one parametric deformation of the Chiral measure of a special kind of representation theoretical type. So this is what we do, this is what we study, where V is the nth tensor power of C2. So now we have a deformation of this, of the Chiral measure, the same question as for H equals 0. So how does this distribution behave when n goes to infinity? So then there are several cases, and so we already, so H equals 0, we know. So suppose that H is fixed and H is greater than 0. So then it's very easy to do this. So all you have to do is you have to compute the asymptotic of the Catalan numbers and use the formula for the characters. And again, this is just very simple exercise for an advanced undergraduate student or for graduate student. And then you get the following answer. Instead of the Gaussian distribution on R3, on the Lie algebra of SO3, or kind of more precisely the radial part of it, which is non-Gaussian. So now we got a really Gaussian distribution in these variables. And the picture that we have is roughly the following. So we have possible spins that occur in this tensor product that are from 0 to n over 2. And there is some special value of this, of the highest weight of the representation of the spin, eta n, where eta is some number that I will explain how to compute. So, and then there is a Gaussian distribution around this limit shape. So I call it a limit shape because it's more or less the same limit shape as maybe you have seen. There are dimer models where which can be reformulated in terms of random surfaces, and then these random surfaces behave beautifully for large systems when they develop the deterministic limit shapes and then they fluctuate around these limit shapes. Basically, generically, the fluctuation is Gaussian, given by conformal field theory, the same conformal field theory that is in the Ising model. So this is the simplest model of this, when the limit shape is just a number, and the instead of conformal field theory, you have the Gaussian distributions, Gaussian fluctuations around this number. And if the representation is somewhere here, sort of macroscopically away from this limit shape, then the probability of this event is exponentially small. Okay, so so this is the, and again, this is the weak convergence. So we have to take a test function, we have to take its expectation value with respect to this probability measure, and then this theorem says that the expectation value of the test function converges to the expectation value with respect to this measure. Okay, so how to compute the limit shape? There is something that's called, in probability theory, it's called the large deviation rate function. In physics, it's called free energy, and it has many names, but the bottom line is that if you take this function where G is the Legendre transform of this simple expression, then eta is the critical point of this function, and this function is convex, so there is only one critical point, and this is where this function is maximal. And as I mentioned, this is a weak convergence, so we have this nice result that the character measure for generic h, that is for h greater than 0, fixed in the limit as n goes to infinity, it converges weakly to this Gaussian measure. Okay, so that's a nice result. So then we can ask the question, what happens to this distribution, to the character measure, when n goes to infinity? But you see, so from here we can learn something. So the size of these fluctuations is of the order square root of n. This is the scale where we have the Gaussian fluctuations. This is the limiting random variable. So you can see that if this eta, if it will happen that it's sufficiently close to the origin, then it will be a special case when the distribution will be so close to the origin that this Gaussian distribution, this Gaussian sort of square root will hit the origin. So that's another special case. When h goes to 0, at this rate, and it's at this rate because of what I just explained. And then if we will rescale, so we'll consider how the distribution looked at these scales, we will have again the weak convergence of the probability measure to this shifted measure that we have for when u equals 0. And if you pass to the limit u equals 0, you will go to the Chiral measure. Okay, so that just says that we have a weak convergence. Okay, so now let's notice the following, that the representations that occur here, they are not completely arbitrary, but they are between 0, they appear with values between 0 and n over 2. So so far all our computations were resulted with the distribution being either square root of n or square root or n times eta plus a square root of n. And this eta, if you look at the computations, it was always fixed and strictly less than 1/2. So now you may ask the question, is it possible to have such a limit when the limit shape is somewhere around n over 2? And yes, it turns out that there is such a limiting process. It's the limit when h should go to infinity as n goes to infinity at such a rate that n times e to the minus 2h is fixed. It's denoted by theta. And then, we get the Poisson distribution on the so now this is n over 2, and then we get the Poisson distribution for these discrete values of L. So in other words, we still got some meaningful answer, but it's again, you can see that it's of different nature. All right, so these are all kind of rather straightforward results that you can obtain by rather simple computations. So now let's change the paradigm, and let's ask the question, why these distributions are so special? What's so special about the character measure and the Chiral measure? And they are special because of the following. So let's multiply those representations one by one. So first we take the decomposition of C2, tensor C2 to C plus C3. So this is L equals 1, L equals 1, L equals 0, L equals 2. And then we multiply C2 by the result, say C3 times C2, C blah, blah, blah. So well-known fact that if you multiply representation of SL2 of spin L times two-dimensional representation, you get two irreducibles. And this gives some kind of natural reason why we should consider lattice walks. So this formula for the tensor product of representations, if we started with L, we can go either to L minus 1 or to L plus 1. So that tensor product motivates this natural question, how the random walks, how the lattice walks behave for n as n increases. And naturally there is a parity involved, say when you take C2 to the even, you will get only the direct sum of even, and then if you take C2 to the odd numbers, to the odd, you get only odd, and so on. So the question is, say, so now we can count the multiplicity simply as the following. So the multiplicity of VL is equal to the number of lattice walks, 2L. So this red lattice walks. So the question is, how can we compute the number of red lattice walks? How can we get this formula for the Catalan number? It turns out there is a very simple reflection principle, which counts the number of lattice walks restricted by the condition that you cannot go to the negative areas. So you can only stay with 0, 1, 2, 3, and so on. So reflection principle, it says that the number of paths that don't cross this kind of line that separates negatives from positives, it's equal to the number of all possible walks from the origin minus the number of lattice walks that start from this point, And that's why you have this formula. And the number of total walks, it's very easy to compute. It's a binomial formula. So you use this formula for the number of total walks, and then you have to subtract the number of walks, total walks from this shifted point. And that's the formula for the multiplicity. That's the Catalan number. Okay, so we have the interpretation of this multiplicity in terms of random walks. Now, what is the significance of the Chiral and character measure? Well, if you fix a Markov chain, some Markov random process on these random walks, it will induce you some probability measure at the else on each step. So this rule, if you take the character of both sides, say character x, character 1x equals to the character L plus 1x plus the character L minus 1x. So clearly it gives you the probability. If you will divide by the, so it's character L divided over character, character L plus 1 divided over character. So these are both non-negative numbers, and you can interpret them as the probability. So together with this decomposition rule, you also have the Markov chain. And if x is 0, this is simply the Chiral measure. And what do you know about the Chiral measure? Well, it's given by the dimensions. So then for large n, what happens if the random walk wanders to some large L's? You see, if you take large L, then these probabilities are approximately equal to 1/2. It just means that this random walk, so this is this so-called Pascal triangle. So this random walk, it starts here and then it goes down on the average. It never crosses the line separating negative from positive, but on the average it goes the same number to the left and the same number to the right. And for the character measure, so sorry, I denoted character Lx. It's the same as chi Lx. So for the character measure, it's the same, but you see, if L goes to infinity, you just take the limit of characters, you get this number for the transition to the right and this number for the transition to the left. And what it means is that when h is positive, there is a drift of this probability measure, and it drifts to this point. And you know, if you draw the straight line from the origin to this point with the average slope given by these probabilities, you will recover exactly the formula for eta. And then all our special cases, other special cases, it's just the following. If h is 0, as I said, then the random walk goes down. If h is of the order, if h is of the order 1 over the square root of n, well, it still goes down almost at the same rate as h is 0, except you will have the center of this, in this case, will be somewhere here. And finally, if h goes to infinity in such a way that this theta is fixed, this random walk will be forced to do very long stretches of going straight to the right for a very long time. Then it can jump by 1 to the left, then again, very long walk to the right, and then finally many steps like this. And that's the Poisson process. Okay, so this is all about SL2 spin 1/2 if I'm a physicist, and it's the highest weight equals 1 if I work in representation theory. So now we finished with kind of physically motivated problem. Now it's a mathematically motivated problem. We're passing from SL2 to any simple Lie algebra, having in mind that SLN is a very good example. Nothing happens for other simple Lie algebras in a way sort of more dramatic or different than it happens for SLN. So any questions at this time? All right, so then let's switch gears. And so now we want to look at what happened for simple Lie algebras. SLN would be typical example. And let V nu be an irreducible finite dimensional G module with the highest weight nu. So if we take nth tensor power of V nu, we get, again, because finite dimensional representation theory is semi-simple, we get the direct sum of irreducibles. And then we have the character measure, and the Chiral measure is a particular case when h equals 0. But now, of course, h is not a scalar. It's an element of the Cartan subalgebra of G. And it's an element of the real Cartan subalgebra for G in order for this to be a probabilistic measure, because we certainly want to have it non-negative and we want the sum to be 1. So both of these conditions will be guaranteed. And this is the probability measure again. Naturally, it's only on the support of the multiplicities, multiplicity function, in other words, only on those representations which occur in the tensor product of, in the nth tensor power of linear. So what do we know about the multiplicities? Well, first let's look at what do we know about character. Well, it's a character of a finite dimensional irreducible representation of G. So we have the Weyl formula for the character. And the question is just the same as before. As n goes to infinity, what is the limiting distribution on invariant tensors, or in other words, on irreducible submodules? Okay, at this point I have to explain some history of this problem. So, I mean, there is a special history in statistical mechanics but here I will focus only on the mathematical part of the history. So Kerov and Vershek and Logan and Shep in 1977, they studied similar problem for the Chiral measure on the symmetric group Sn as n goes to infinity. It's a similar problem, but of slightly different flavor. And then Kerov in 1986, he studied Chiral measure on the nth tensor power of the fundamental representation of SLN. Again, this is the case when multiplicities are all known. They are given by the formula for dimensions of the symmetric group Sn capital, and they are given by those dimensions because of the Schur-Weyl duality. So he studied this measure. Then Philippe Bien in 1993, he looked at the asymptotical behavior of multiplicities as n goes to infinity. Tata and Zeldich in 2004 studied Chiral measures and lattice path in this v to the n, just continuing the work of Bien. So then with Olga Postnova, so we studied character measures for generic H. Generic meaning that H alpha is greater than 0 for any alpha in the positive, for any positive root for the Lie algebra G. It's the analog of this condition that H is strictly greater than 0. And then with Olga and Vera, so we studied the character measures for all possible H for generic, that is when H is strictly inside of the principal Weyl chamber, and the non-generic cases are when it can be on the walls of the principal Weyl chamber, and the most most singular case, that's the Chiral measure. So it's a very natural question, and the paper is almost ready. It's just that we just have to finish writing, and it's just it should be ready soon. So in order to compute these distributions, all we have to do is we have to find the multiplicities, the limits, the asymptotic of the multiplicities, and use the asymptotical formula for characters. So somehow, so we decided to recompute the asymptotics of multiplicities, simply just to simplify some of the previous work. So we didn't do anything very original, just use the orthogonality of characters. So this is the usual orthogonality of characters. So here the delta is the Weyl denominator. This is the radial part of the Chiral measure. This is, Haar measure. This is the Haar measure. And we use the basis of not dual roots, co-roots. So, and then the multiplicity, if you just use the orthogonality, use the formula, Weyl formula for the characters, it will cancel one of the deltas in the radial measure, and that's the formula. So all you have to do now is you have to use the steepest descent method and compute the asymptotical behavior of this measure. So now let's assume that Xi is generic and finite, and lambda is proportional to n. If you want, this is motivated by the fact that for SL2, we have this behavior of the, so this is where the limit shape is. So So it's natural to find the asymptotical behavior of the multiplicity in this region for these values of lambdas, and then use the machinery to compute the asymptotical behavior of the probability measure. So then it's not very difficult to derive the following asymptotical behavior of the multiplicity. So this is just the result of the steepest descent computations. I'm not going to overload you with the details. You'll find it in the paper. So here again, as you see, it's very similar to what we have for SL2. So it's just the Legendre transform of the logarithm of the character. And say if a physicist would do this problem, this is where he or she would start and would just do some kind of physical mantra and would recover the correct asymptotic. But in order to prove it, you have to do some hard work, and this is what we did. Okay, this is what Philip Young did, this is what Tate and Zeldich did, and this is what we did as well. So this is the first step, the asymptotical behavior of multiplicities, and then let's use this result to compute the probability of the limiting probability measure, and this is what we derived with Olga Pasnova. So if H is generic, then the limiting probability is Gaussian. It's given by this formula where K is, well, it's the matrix of second derivatives of the rate function. So if you go into the computations, you will see that it's all natural. And then the probability of being macroscopically away from the limit shape is exponentially small. Okay, so this is very similar to SL2, and again, this is the eta is the maximizer of our rate function, and this means that we're talking about the weak convergence of probability measures. And now let's look at what happens when H is on a wall of the principal well chamber. So in this case, we have a natural. So if you fix this particular wall where H is, it just means that for some roots, positive roots, the component H alpha is 0, and for some positive roots, it's positive. Those for which it's 0, it's a root system for a Lie subalgebra of G, and this Lie subalgebra it's a root embedding, so the diagram embedding, Dynkin diagram of G0 is embedded into the Dynkin diagram of G. So let's say that R0 is the rank of our Lie algebra G0. So then for the character, for the asymptotical behavior of the character as n goes to infinity, it's a theorem. It's not very complicated theorem, but it's a theorem nevertheless, that from the Weil formula for the character, we derive the following, that there will be this prefactor, then something that will go to the rate function, that's this part, something that will remain finite, something that will remain finite that doesn't depend on H, and some factors that depend on H. So this is the behavior, and then for the asymptotical behavior of the probability measure, we have to split the Cartan part, I mean, Cartan's subalgebra naturally into the G0, into H0 part and H1 part. In other words, the result that I will describe first requires that we consider the weights of the following type. There is this n times the limit shape. This is where the measure is concentrated. And then the distribution around this point is the weights around this point are distributed at the scale of square root of n. And the distributions are different in the orthogonal direction to the wall and in the parallel direction to the wall. In other words, here A we choose in such a way that alpha A is 0 for alpha in delta 1, and alpha B is 0 for alpha in delta 0. So this is the first technical part. Second technical part. So V nu is an irreducible G module. If we will restrict it to G0, G0 is this sub-Lie algebra of G that's determined by the choice of the wall. So here it's this choice of the wall, so it's the corresponding SL2, if this is SL3. So then, again, it decomposes into the irreducible representations of G0. The restriction of H to G0 is 0 by definition, because H is on this wall. And then and this is what we get for, and then let's define this number. It's a kind of ugly number, but you know, so if you think about it a little bit, it will have a perfect meaning. And then the theorem that will appear in our paper is the following, that the character probability measure for this degenerate values for these singular values of H, it converges weakly to the product of probability measures. One is the Gaussian probability measure in the directions along the wall. And then the other is the limiting Chiral measure of the radial part of the Gaussian distribution on the corresponding Lie algebra. So that's in the orthogonal directions to the wall. So if we will denote this first factor as P1, the second factor as P0. So what I just said is the following, that if we take this, if we take a test function, subtract the limiting, sorry, the limit shape, divide by, for the normalization, divide by the square root of n, then this expectation value converges as n goes to infinity to the product of two measures that I just described above. And so this is and this completes the description of this asymptotic representation theoretical problem for all values of H in the character measure. And then similarly, I'm not going to talk about this, but it's not difficult to see what happens if you are not on the wall. If this H, so you see, this is the wall, this is where H was before, and now we can assume that H is somewhere here with the distance of the order square root of n, or rather 1 over the square root of n. Then we get this deformation of the of this process. So this process gets deformed by U. It will be some interesting answer. And then again, there is a room for interesting behavior when n goes to infinity. When h goes to infinity, then we get the analog of the Poisson distribution. But again, now h is not a number that can go to infinity, it's a vector, and it can go to infinity in some directions. It doesn't have to go to infinity in some other directions. So there are some special cases here. And then what I really wanted to talk about, but I hope that this story was also interesting, is a similar story for representations of quantized universal SL2 when Q is a root of unity. We consider quantized SL2 with divided powers. And in this case, two-dimensional representation is an irreducible representation with the highest weight 1, but it's also a tilting module with the highest weight 1. And then the problem in this case is we take the tensor power of this tilting module, and then we want to compute the decomposition of this tilting module into the tensor product, into the direct sum of tilting modules with some multiplicities. And then it turns out that there is a very interesting counterpart to all this story. The difference is that the lattice walks will be different. They will depend, say, on the degree of the root of unity. The statistics will depend on the degree of the root of unity. And then if you are creative, you can imagine that if you have a vertex separator algebra that's not semi-simple, that's related to tilting modules of UQSL2, then if you have the expectation values of lots of vertex operators, this might tell you something about the behavior of these large products of vertex operators. Thank you.
So are there any questions? Maybe from the Zoom audience? Okay, so I thought the talk was very interesting. I don't really have any questions, though.
It's probably... There was no vertex operators.
Yeah. Well, they should be there in the background somehow.
Yes, they are in the background.
Well, okay, so if there are no questions, then let's thank the speaker again for a very beautiful talk.
Thank you.
What time is it there, by the way? You're in Beijing.
Oh, it's 9 p.m.
9 p.m. Oh, yeah.